Hello and welcome to my channel. Today we'll be exploring a very important yet often misunderstood topic in the valve industry, that is cavitation in control valves. Whether you are a valve engineer, a maintenance engineer or just curious about fluid dynamics, this video is for you. Before we start and discuss about cavitation, I wanted to discuss briefly about control valve. In control valve, there is always a pressure drop, and this is how a control valve works. It means that P1 will always be greater than P2. For some application, delta P is less, while for other, delta P is more. Now, let me explain what is cavitation. Cavitation is a phenomena that occurs when a liquid local static pressure drops below its vapor pressure, causing it to vaporize. These vapor bubbles then collapse violently when the pressure recovers downstream, thereby creating shock waves. This implosion can damage the valve internals, reduce performance and cause noise and vibration. In control valve, cavitation is most common in high pressure drop application such as in pump discharge throttling, boiler feed water system and process control in high head lines. So here we will try to discuss about when cavitation occurs, what should be our selection for the trim and the material to handle the cavitation. Also we will take the help of the standard ISA S75.23 to understand it better. In the standard, they introduce a term called sigma, which gives the indication of cavitation and is calculated with the formula as shown. Do note that the unit for the pressures are in absolute terms. Now let us consider a scenario where delta P is changing. As you can see, as delta P is increasing, the value of sigma is reducing. For simplicity, we have kept the numerator constant and try to increase the denominator. However, temperature also plays a critical role in calculating the sigma value. If the temperature increases, vapor pressure will also increase, thereby even with lower delta P, the sigma value will be lower and cavitation may occur. So this sigma value is calculated based on the process parameter. Also there is a sigma MR value which is for the valve and obtained by testing in a lab. So ideally sigma MR should be lower than sigma process, so that even when cavitation occur, the valve will able to handle that pressure drop. Now for the sigma MR, with the guideline given in the ISA standard, the sigma MR value is obtained from a test valve of a particular size with a specific trim and test pressure, and hence we cannot compare directly with the sigma process value. We need to consider the pressure scale effect and the size scale effect, also the pipe correction factor, to get the new sigma value. The new sigma value will then be compared with the sigma process value, and as obviously the sigma P, that is the corrected value, must be lower than the sigma process value. Now imagine a scenario where sigma process is 1.5 while the sigma MR is 1.3. However, we need to evaluate the corrected sigma value, then compare it. If the value is less than the sigma process, we need to take a different trim with a sigma value lower than 1.3. You can see the same in the assumed calculations. Complete calculation is available in the ISA standards and you can refer to it directly based on your exact requirements. One other important thing which I wanted to mention is that there are other scale factors which are not considered. However, it do affect the intensity of the cavitation. Those are viscosity, velocity, dissolved and undissolved gases in the liquid, thermal property of the liquid and duty cycle. Do note that the test is being done on water, and hence if the media is different, the properties will come into the effect to give you the exact value. Once the suitable trim is selected, you can calculate the damage intensity. Here, as you can see in the equation, there are three factors. The first one is Fu, that is the velocity factor. This depends upon the velocity in the valve. Okay, if the velocity is very high, then Fu value will be much higher. The second one is Ft, based on the different temperatures of the media. This value is calculated. The third value is FDC, that is duty cycle factor. This factor depends upon how frequently you are opening and closing the valve. Based on this FDC value is being obtained directly from the standards. Once these values are obtained, you have the sigma id that is coming from sigma r, and you have sigma ss that is coming from the process calculated value. Once you have these available values with you, you can calculate the value of I. If the I value is much higher, for example, if the value of the I is 2.5, it means that the material will erode at a rate of 2.5. So in order to reduce, you need to have a hardened material where Fu value will reduce drastically, thereby your I value will reduce. With this, we come to end of our presentation. If you are looking for a valve where cavitation occurs, do contact us and we will be able to provide you with the valve. Thank you.